One. So we have a few questions from 2024 chapter competition. So this was a sprint number 26. So we are looking for the sum of the all positive solutions. So let's highlight this part of this equation. We have like a bunch of parentheses, and we don't really want to expand them because this is the first degree, second degree, which will give us a fifth degree polynomial if you want to expand them. And then if you expand these guys, you will get also a third degree, and subtract, you will have a fifth degree polynomial, which is not easier to deal with. So instead, maybe we can try factoring the parentheses and see if we can get something better. So the first one is x minus 1. So that's the first case. And then the second one, we have -2 and the coefficient of the linear term is 1. So if you factor those, so that will be x plus 2 and x minus 1. Okay, if you are not sure how to find like factors, you just basically look for two numbers to multiply to get this constant and add to get the coefficient of the linear term when the square term has a coefficient of 1. And that's basically what I did. And the next one, now we have 6 and -5. So I can just say this is x minus 2 and x minus 3. And this is equal to 12 times. So this guy would be x minus 1 and x minus 3. And the last one is already binomial x plus 2. So, we have x minus 1, x minus 1, x plus 2, x plus 2, and x minus 3 and x minus 3. So if you like to kind of cancel these factors, we can, but at the same time, we actually eliminate some of the solution when we do so, right? And then we cannot really do it because it's not gonna be helpful. So if I just pull everything on one side, so you will get x minus 1 times x plus 2, x minus 1, x minus 2, x minus 3 minus 12 times x minus 1, x minus 3, and then x plus 2. So this is equal to 0, right? So now we do have some common terms. So x minus 1 is common, and x plus 2 is common, and then x minus 3 is also common. So which means we can pull these binomials as a common factor. If I pull these, so x minus 3, then the remaining part that will be left over. So of these 5 like binomial, I pull everything except these two. So that should give me x minus 1 and x minus 2, and then minus 12, and then I took already these, so that should be my all the second part. And the product is equal to 0, so that means if I simplify this part, so you will get x times x will be x squared, x times this -2x, and then -1 times x is -x. If you combine those, you get -3x, and then -1 times -2 is 2, so 2 minus 12 is just -10. And then this is equal to 0. Now we have x minus 1, and then x plus 2, and x minus 3 is equal to 0. So if I want to factor this guy, then this is also factorable because this is like -2 times 5. And then if you add, -5 times 2, so that will be x minus 5 and x plus 2. And then this is equal to 0. So then x minus 1, x plus 2, x minus 3. So if the product is equal to 0, each one of these binomials might be 0. So if this is 0, x equals 1. And if the second one is 0, x equals -2. And if this is 0, x equals 3. And x equals 5. And x equals -2. So we don't want to add everything. We want to just add the positive ones. So which is 1, 3, and 5. If you add these, you do get 9. Okay. So this wasn't too challenging as long as you are careful with your factoring. I guess this was a fairly okay for number 26. Okay, so let's look at the next one. Number 27. So the Albert has a meeting at 4, and then he leaves the house in between 3 p.m. to 3:30, and then the traffic takes about 30 to 45 minutes to get to the meeting from his house. And we want to find the probability that he's going to be there early. Okay. So like it's a classic geometric probability problem. So in these cases, we want to kind of find the area and find the probability by using the areas. Okay. So like to kind of see how that looks like, I'm gonna use the x-axis as his like living time. Okay, and then the y-axis as arriving time. Okay, so like, and then since he is gonna leave at 3 or 3:30, anything in between these two, I'm gonna just divide this region, the x-axis, into some intervals in between 3 to 3:30. And at the same time, like, he can go there in 45 minutes, which is like 5 minutes interval is important in this case. So I'm going to make this 5 minutes intervals. So let's assume the origin is like 3 p.m. So, and then I'm going to continue like 5 minutes interval. So this is 3:05, 10, like 15, 20, 25, and this is 3:30, right? So this is 3:30. And the y interval, I can just start with 30 whatever place. I'm gonna go ahead and say, let's say this is 3:30, right? I'm gonna go with this is 3:30. And maybe I should consider this is 3:30. That might be a bit better. So let's go with that. So this is gonna be 3:30, arriving time for this guy. And then this is 35, 40, 45, like 50, 55, and 60. This is gonna be 4 p.m. and 5, 10, and 15. This is 4:15. So we don't need more than that because we are gonna get there at most like at 45 minutes. If he leaves around like 3:30, that will be 4:15. So now like we can just write some equation for this case. But for now, I'm gonna just dive into with some basics, plug in numbers. If he leaves at 3, right? So he's gonna be there in between 3:30 to 3:45. So this is 3:30, right? 3:45 is right here. So this is the interval that he will be there in between these two, right? But if he's leaving at 3:05, so then he can be there 3:35 to 3:50. So if this is the case, that will be 3:35. So this is 30, this is 35. So right there, 45. So this is 50. So mine is not really scaled. So I hope that will make our drawing a bit accurate, but that's the case. And if he's leaving like 3, let's say 10, then he's going to be there 3:40 at least, or 3:55. And if you keep doing that, so 3:15 he's leaving, then he might be there at 3:45 all the way to the 4 p.m. So let's write these as well. So if this is 3:10, he's gonna be there 3:40. So that is 40. So something right there, all the way to the 55. So then this is gonna be the case. And I hope you see the pattern. So since this is gonna increase linearly, so you do expect a straight line, which looks like you are getting already. And if this is like 15, that should be 45 to 4 p.m. So that should be 45 is right there. And then this is gonna be 4 p.m. So that is exactly at 4. And if you do this 3:30, so you can continue doing this like 3:30, then that will be 4 p.m. to 4:15. So that would be 4 p.m. is right there, and then 15 is somewhere right there. So that's the case. So now I hope that is obvious. If you kind of see this a bit earlier, then after plugging this many line, you can just try your straight path without expanding more points. But I think we are good with this. So that is the region basically. And the question is asking, find the region where then he's gonna be there before 4 p.m. But one more thing before I get to there, we can just make these lines by using the a bit smart approach, I would say. This is x and this is y axis. And now we know whenever you start at 3 and then he can go there in 30 minutes, which means it has to take at least 30 minutes. So which means the y value, right, is at least 30 more than x value. So I can say x plus 30, which is gonna be when you add 30 minutes, that will take the y value. So that means y value should be at least this much, right? It could be equal. And also it will take at most 45 minutes. So which means the y value should be lesser than x plus 45. So you can just kind of write these equation and y equals x plus 30. So if you want to go with that, so you are gonna like draw a kind of like 30 first. I just start with origin, which doesn't make any difference, but I could have done this way as well. And then my graph right here is gonna be a bit like above right there, but overall it doesn't make any difference. Okay, so you can use that as well. But now we want to find the region that is gonna be lower than 4 p.m. And then we know that when this is 3:30, that was exactly 4. So which is why anything that is lower than this in this parallelogram is what we want, and above is what we don't want. So like this was 3:15. So if you remember, which is just right in the middle, which is why it's kind of nicer. And then this region and then this region is equal to, if I say this is A, then this is also A, and then this is gonna be parallelogram. And then the area of this two is actually the same as area of the remaining parts. So even though it doesn't maybe look like, but it is. So if I just connect this way, so that will be equal. So then we have 4A in total. And then of these 4A's, one of A is not what we want and anything else is what we want, which is why that will be 3, 4. So I hope that was clear. So you can approach this problem a couple different ways, but I think that is okay as well. So let's look at the next one. Number 28 now. So what is the least 9-digit positive integer that contains the digit 1 through 9 exactly once, and that's divisible by 99? So first thing we need to remember, like in order for a number to be divisible by 99, should be divisible by 11 and 9. And then digit sum should be a multiple of 9 in order for that to be divisible by 9. And then if you are using 1 through 9, like, if you use the Gauss formula, like you will get all the way to the 9. And if you add these, so 9 times 10 over 2, which is 45. So the sum of the digits is actually 45, which means that's already divisible by 9 for sure, regardless of what order you write those. And we just need to satisfy the 11. So the rule for 11 was when you take the positive difference between alternating digit sum, that should be multiple of 11. Could be 0 or could be multiple of any multiple of 11. So since we know the digit sum is 45, so you're gonna have two different groups. So let's say 1, 2, 3, 4, 5, 6, 7, 8, 9. And then when you make two different groups, because you're gonna add them alternately, then you're gonna have 5 numbers in one list and the 4 numbers on the other list. So some of them will not be equal to each other, because if you divide this by 2, that's not gonna be a whole number. So which means we cannot have this sum to be equal. So that means the difference should be 11, okay? Or maybe 22, which is not possible. But if you think about this sum to be like difference between those two sum is 11, I hope that was clear, then I can subtract 11 from 45, which is 34. So that means the half of this one will be in 5 whole numbers, and then other half will be with other 4 numbers, okay? So that is 17 plus 11 will be one of the list, like one of those like sum, I would say, which is 28. And the other one should be just 17. Okay, so again, if I want to try adding the smallest 5 numbers, for example, to see if this is possible with 17, 1 through 5 is just 5, 6 over 2, which is 15, right? So that is still possible, but I think we cannot really achieve that. So which is why we are gonna go with like smallest number I mean, the sum of the five numbers to be 28. So to get the smallest number, I'm gonna go with 1, 2, 3, and 4. And I will stop here because what we care is the leftmost numbers should be as small as possible. At the same time, we should satisfy the sum of the alternative sum should be 28 and 17. So like if I add this guy and this guy and this guy and this guy, the sum of these four numbers should be 17. So we have 2 and 4, which is 6. And if you subtract from this, you get 11. So the sum of the other two digits should be 11. But if you want to get the smallest, so this has to be 9, this has to be 4, but there's 4 right there. We cannot go with that. So we should get at least 5. And then the other one should be 6, right? So that is going to be now 6. And the goal is just to make the as small as possible for the other digits. So what we use already 1 through 6, so that should be 7, and this should be 8, and that should be 9 as well. So let's double check 1, 2, 3, 4, right? And then 7, 5, 8, 6, and 9. I think, yeah, this is the case. And if you try some other ways, like if you kind of ask yourself, like, how do I know this is the smallest possible? Because if I try like 1, 2, my next number, like if I change this to 5, then that's going to be already bigger than what we have already. So which means I can just go as low as possible with 4. As soon as this is possible, now I need to pause a minute there and then see how do I end this, because the alternating digit sum should be 17 and 28. So then the four of these numbers should be smaller one. Otherwise, it doesn't like satisfy anyway. So which is why I should get 17, and then we got already 2 and 6, which is, I mean, 2 and 4, that's 6, and then subtract that, that's 11. So other two remaining numbers should be 11. And then that is the only way that's possible. I mean, not the only way, but easy, like smaller way is 5 is to the leftmost number, and then 6 is right here. And when you complete the rest, this is what we got, okay? So that is 1, 2, 3, 4, 7, 5, 8, 6, and 9. So this wasn't too challenging, to be honest, but it's kind of is not easier to see immediately. So that was a nice divisibility problem. I hope that was clear. I'll see you in the next video.